Okay, everybody, good afternoon and welcome to this session. My name is Anil Kokaram. I am the head of Department of Electronics and Electrical Engineering here at Trinity College. And I'm going to be talking to you about the continuum between electronic engineering all the way across to computer engineering. So, in fact, right now we have 3 degree programs, one in electronic engineering, one in computer engineering, and one in the electronic and computer engineering. So yeah, there is this continuum from electronic system design, hardware design on one side, all the way across to software design on the other side. These distinctions, you know, over time have become very nebulous. And so by the time you come to do this degree program, we just probably have one label and you could choose where you want that dial to be in this continuum. So in my experience, you know, there are sort of 3 things that people want to know when they come to talks like these. First of all, what is the career prospects like in this discipline? So are there any jobs in this stuff? And then what's in the course, and of course, what is electronics anyway, and how good are we here at Trinity College? So I'm going to kick off with that first question about jobs and careers. So just to give you an example, before I start talking about these companies, right now we have an internship program in the 4th year. In that internship program, students could go away for 6 months, go away as part of their degree, working with companies here in Dublin in the electronics sector. And right now we have more companies asking us for interns than we have students on the program, right? So there's a huge demand for our graduates right now. To give you another example, this company Xilinx, they are the most significant company in the world for developing something called reconfigurable hardware, which you would actually find this in almost every piece of electronics you have in your home, and increasingly these days in data centers and so on, in cars, everywhere. And their headquarters is here in Ireland. They've just been acquired by a company called AMD. And AMD is the main competitor for Intel. So now here in Ireland we have the European headquarters for 2 of the most important CPU manufacturers worldwide. Intel have a huge manufacturing plant just outside Dublin and Leixlip, and AMD are setting up operations now centered on Xilinx. So there are huge career prospects there. Recently, Intel also acquired a company called Movidius, which makes sort of deep learning, artificial intelligence hardware. And the spin-out was created by one of our former graduates, and many of our electronics graduates work there. Qualcomm is another pretty big company. If anybody here has a mobile phone on them, which most of you do, 70% of the kit in that phone is made by that company, and their headquarters is growing down in Cork. And finally, for reasons I'll talk about later in this course, especially in the video infrastructure teams of YouTube and so on, you'll find a handful of our graduates working there. And over the years, electronics has become so diffuse, especially the automobile sector has taken advantage of the advances in consumer electronics. So quite a lot of your car control systems now based on electronics design, controls, robotics, a lot of video equipment in your car. Jaguar Land Rover moved their software engineering site from the UK to west of Ireland a couple of years ago, and they're still hiring. Valeo is a big company making electronic parts for cars, and they're also based out in Galway. And just to give you another example, there's a picture of me with some of our research assistants in my group. They just recently graduated, and now Kieran is in Berlin working for a company called Synference.bio, and he's designing new drugs and looking for ways to fold proteins Sophia, she's based in Dublin now, working for a company called The Foundry. They are one of the most important producers of software for the cinema special effects industry, and their R&D department is headquartered actually in one of the offices in our building. And Sophia is working on new tools for special effects. Vibhuti has just joined us, and in fact he is working on research with YouTube and Netflix, and hoping to join the Netflix video infrastructure team next year in California, working on video processing research. So electronics and computer engineering covers a pretty broad span of things, and there's certainly careers available. In Trinity College, electronics and computer science has a strong reputation. We are the #1 department in electronics and also computer science in Ireland. Certainly, we both rank very highly worldwide. And the engineering school is in the top 150 in the world. All our degree programs are accredited by Engineers Ireland. And in 2024, we are about to launch an entirely new building called the E3 Learning Foundry, specifically targeted at undergraduate education. Now, in my department, electronics engineering, we have groups in these particular areas: signal processing, digital communications, biomedical engineering, robotics, and circuits and systems. Signal processing, control, and digital comms in particular are sort of implicated in this new area of AI and deep learning and so on. Just to give you an idea of what this new building is going to look like, it's very close to here. There's a big missing slot in the buildings if you go walking that way, and that will be filled by this 6-story E3 Learning Foundry in 2024. And I have a short video here which should show you what it looks like.
The E3 vision takes physical shape within a 7,300 square metre building, the Martin Naughton E3 Learning Foundry. This new structure will serve to form the learning of our students and to mould them into the leaders, creators, investigators and innovators.
You get the idea. You can see that on YouTube, right? This brings me to that last box, right? What is electronics engineering, and what happens when you come to take the degree program here? What sort of things do you do? And you know, there's nothing that could replace you speaking to people with experience in electronic engineering careers, because so to give you an example, we have 16 staff in this area in the whole school, and if you talk to each one of them, they have a different way to express what they think electronics and computer engineering is. So we started to interview these people, and we've created these short clips that you could find on YouTube. If you take a picture of the screen and go to that QR code, that has that web address, and I really encourage you to have a look at these little clips. It's the best way to find out exactly how broad this area is and how people come to do the things that they come to do. So it turns out, so Naomi Hart, she's one of our senior academics in an area called speech processing, and what she has to say actually is kind of similar to what I say in that clip, and I'll let her say a few words here.
I was never one of these kids who was always interested in engineering. I definitely had a strong like for maths in school. I liked science. I liked understanding how or why things are so. And I did consider studying maths for a while, but what attracted me more about engineering was the fact that you could apply it to things, that you could solve problems. You didn't just get to understand how things worked, but you could change things. You could make new things from that understanding. Then as an undergraduate, I discovered signal processing, and the fact that I could use that to understand a signal like speech really resonated with me. It wasn't just maths, it was actually understanding something so basic to humans as talking to each other.
So her clip actually is similar to like I say, what I say, and we have had sort of similar experiences. Dan Kilper is another really interesting clip. He is a recent professor, just joined us from United States. His work is in telecommunications. He runs the biggest telecommunications research center here in Ireland, and he's well connected to several National Science Foundation initiatives over in the States, including a big initiative on 5G and 6G and so on in New York. So students that work with him, they get to work with similar teams over on the East Coast of the United States. And he talks a bit about that in that clip. So I'll encourage you to look at these things. So now I'll give you my story, my spin on what electronics and computer engineering means to me, and maybe it'll help you figure out what this is all about. And at this point in the talk, I generally pause and recognize that people get a bit confused with my accent, and I want to point out I'm not from here, that I'm actually from here, a place called Trinidad and Tobago. And the next thing you want to know is why I would leave a place that looks like this and go all the way here to a place that looks like that. And that's another long story. But also important for this talk and my experiences, I spent about 5 or 6 years working in the video infrastructure research teams of Google/YouTube. And that caused me to sort of think differently about what university education is for and how it should link with how you could affect the world and so on. And it's sort of reflected in some new initiatives that we have in the department over the last few years. So to talk about my experiences, then my research is in a thing called signal processing, and specifically in video processing. And if you want to dig down further, it's actually on just making old pictures look like new. So we are interested in enhancing pictures, making better streaming video, and so on. And I land somewhere between hardcore electronics, hardware design, and totally software design, right? Somewhere inside that, in that continuum. Now, these days it's a lot easier for me to speak about video technology to people because the last 3 years, video technology has become pretty important for everyone over the last 3 years. And just to give an example, that big peak there was the peak in searches on Google for Zoom and Teams and Hangouts and so on. So you can see just as the pandemic started, everybody went online to figure out how to use video to do streaming and still go to work and look at your lectures online and so on. And it's really thanks to a lot of motion picture engineers over the last 10 years working on the fundamental problem of how to stream video and data over the internet, which wasn't built to do that in the 80s. How to stream that stuff and make it arrive to you in good time and good quality and so on. It was because of that engineering effort that the world didn't shut down for 2 years during the pandemic. You were still able to do work. We were still able to educate students over the internet and over streaming and so on. And universities didn't have to close. So you know a lot more about video technology now than you would have done a couple of years ago, and a lot of terminology I use in class, students kind of know about now. So, in my head anyway, this area of electronics and computer engineering is about information processing. And these days what's happened is we now convert a lot of the observed phenomenon in the world, like temperature measurements of a car engine, or speech or video or electric power consumption in your house. We convert those measurements we convert those observations into discrete measurements, associate numbers with them, and then it turns out that the techniques that are involved in processing those numbers to extract information could be used for any kinds of measurements. And so you tend to start to see the evolution of new ways of thinking about how to control machines, how to predict events, how to enhance experiences by this area of digital processing. And in a way, it's one of the most important changes to the way we build systems in the world since the Industrial Revolution. And to give you an idea of what I'm talking about. Here's a really simple example coming from my research, and I use this example with second year undergraduate students in my class on computational engineering. So here we have 3 frames from an old movie. So this one is the one we're interested in, and this is the one before, and this is the one after, right? And it's an old movie, so there's a lot of grain, noise, and there's these little splodges, these white things called sparkle, and the dark splodges, they're actually dirt stuck to the film. So up till the late 1990s, the only way to restore this thing so that you could broadcast it on TV and so on was to do it manually, which it just doesn't scale. It takes a long time. So we started to look at ways to do this automatically. And if you think about it, you know, these splodges, they are randomly distributed over the frame, and they don't exist in the same place in consecutive frames. So if you see here, this splodge exists here, but it doesn't exist here, it doesn't exist there, so it must be a splodge. Whereas this wheel, it exists here, here, and here, so it must be a thing that is in the movie. So we could start to build a sort of data processing way of thinking about how to do this problem automatically, right? So here are my 3 frames. And what I could do is estimate motion from this frame into here and this frame into here. These vectors represent that motion. And I could look at intensity differences between, you know, this patch and this patch and this patch and this patch. And if I find big intensity differences, like here, I would find a big intensity difference forward and a big difference backward, then I could tell, okay, that must be a problem, and I could do something about it. So here, I have colored all the pixels which have these big differences. I colored them in white. So you can see, in fact, it does do a pretty good job of finding all these splodges, but it also finds some things that we would rather leave alone, like this wing. It's a classic engineering problem, right? The first thing that occurs to you, which is, you know, the most intuitive idea, tends to work like 80% of the time, but then it's the last 20% that really gets things to happen, right? So right now, if we were to use this algorithm to fix this movie, we would remove all the wings in the aircraft, which is not good. So it turns out you have to, you know, dig a bit deeper into this problem. And these days, people think about these problems in these 4 boxes. Okay, you first think about it intuitively. You try to write down some mathematical models that capture the problem. Then, in this case, we used a model which is, you know, things don't change much over time. We used that idea to predict what pixels should look like. And then we decided if the pixels are very far away, they look very different from what we expect, then it must be a problem. And then finally, we use that model to correct the problem. So that system, at that high level, then yields some you know, specific engineering steps, which we could then implement in hardware and software. So these days, that idea is part of this big area called artificial intelligence and machine learning and so on. And electronic and computer engineering is the place where you learn more about that technology. So here's an example of the results from many years of work. On the left is a movie stored in the Irish Film Centre called Rory O'More. It was filmed in 1910. And so on the left, you can see the archive version, which has all those splodges, and it's also a little unstable, and there's brightness flicker and so on. And on the right is the restored picture, which has been achieved by applying a bunch of automated techniques. So we could detect those splodges automatically and remove them. We could stabilize the pictures. And in fact, this stabilization algorithm is something that you have in all your phones right now. And that's how you have stable pictures when you take video on your phone. So my story at that point takes a very interesting turn. Because we were working on that restoration stuff. And then that movie happened in the late 90s. Now, the thing is, I'm quite old now. I don't know how many people actually know this movie. How many people actually know this movie, The Matrix? Oh, it's still popular. Very good, very good. right? So it turns out that movie, the special effects for that movie was done by a company called ESC Entertainment in Los Angeles. And this guy, Bill Collis, was involved in the first special effects and creation of that special effect called Bullet Time. And it turns out that I used to work with Bill in research projects involving video and video restoration. And he came to me one day and said, well, actually, you've been spending a lot of time removing holes in pictures. And doing that is a lot similar to the problem in the movies where, you have to suspend actors with wires and so on. And they would like to remove wires automatically because at the minute that was done manually. So I had a go at solving that problem, and it worked pretty good. And because that worked good, removing small splodges, is a small step to removing the entire frame and rebuilding the entire frame, which is the bullet time effect, right? So in my second year class, I teach students about mathematics using the bullet time effect. And that became really popular, so automating that process. And these are some examples of the first movies to use that automatic technology for building new frames and building new pixels and so on. And by 2007, almost all the cinema post-production houses worldwide were using that motion-based enhancement suite. So in 2007, we were, all four of us were honored to receive an Oscar for that development, because it sort of changed the industry to make it easier to use these sort of complicated tools. And that's a sort of funny thing for a guy working in electronics engineering to say. Being head of electronics engineering here at Trinity is very unusual, and the room now is split into half of you wondering, what was that like? And the other half wondering, no, that can't be true. So here's some pictures. Right. So we were actually there. It did really happen. It was a fantastic occasion, a life-changing experience. Never happens again. And the other thing that people always want to know is if you met anybody famous, right? So here's somebody famous, and this is the closest we ever got to somebody. So anyway, so yeah, that sort of changed a lot of things around that time. But one sort of reason for telling you that story is that hello, it's just like one of my lectures. So yeah, the other reason for telling you that story is up till about 2022, entertainment is the thing that was driving new technology development. Okay, the reason why we have data centers, is not because we want to send people to the moon, it's because somebody wants to do video transcoding for clips for TikTok, right? So in some ways it's sad, but actually it's because of that, the effort to make this new technology to help people play online games, to make computers faster so that you could stream video more efficiently. It's because of that those technologies started to fuel a renaissance into thinking about other ways that we could affect other disciplines, particularly biomedical engineering and health science, right? So all the technology that is used for game playing and the graphics units that synthesize pictures now used for AI and deep learning, which helps diagnose things like retinal diseases and so on. So that push to develop new technology caused a lot of changes, and you're seeing that now in society. In 2022, though, actually over the last 5 years, even just before the pandemic, what was happening was there was so much volume of work especially in video engineering and data centers and so on, that software couldn't keep up anymore. So you had a renaissance in consumer electronics, and then things like the autonomous driving and electric cars and so on caused even more interest in consumer electronics and hardware design and energy consumption. This year, over the last few years, you would have noticed that because of the disruption of supply chains, electronics hardware was hard to get, and that meant funny things started to get affected. Like you couldn't buy a washing machine because all the electronics was being made somewhere else, and all the parts were being held up. You couldn't get a new car the delay times were very long because a lot of cars have a lot of electronics kit in them. So in the last year, the European Union just passed this CHIPS Act to revitalize the industry and bring manufacturing back to the European Union. Same thing with the United States, and that's going to change this industry once more. Sensors have also changed. They become smaller, less power, and so on. There's a company here in Ireland called Boston Scientific. They create or they make a lot of biomedical engineering sensors, even make internal defibrillators for your heart that sense when your heart is about to shut down and internally restart it. There's some amazing examples of that, of it in use. So biomedical engineering, biomedical electronics is another big active area. Okay, right. So last thing is what happens when you come here to Trinity? What do you do in the course? So you would have heard if you went to the general talks earlier today that the degree is a general engineering degree. So you have 2 years of general engineering, so civil, mechanical, and electronics, everybody in the same place, doing the same course, same modules. And then in years 3, 4, and 5, you specialize. So in year 3, you choose one of these 3 strands. And then you could exit at year 4 or go on to year 5 with a master's program, master's degree. Another very interesting new development this year is the first year we have started to kick this off, which is our relationship with Columbia University in New York. So that is the number 16 university in the world when I did this when I looked it up anyway. So in year 4, you could choose to apply to Columbia University. This year we have a handful of applications, and you could finish with a master's in Columbia, from Columbia, as well as Trinity College, which is quite a powerful thing. So the curriculum, the way I think about it anyway, is about really helping you to survive in the age of automation, right? And giving you the flexibility and the confidence to move between different disciplines. We even introduce you to the world of electronic arts and electronic music technology. We have a number of people involved in music and media design and synthesis with new media. And in the first year, actually, they give you a few lectures on what electronic arts and music technology means to them. In the second year, you get to do some kind of early work in robotics, right? So you start, these little buggies are things that you build together with your compatriots in civil and mechanical and so on. And these multidisciplinary teams turn out to be a really good idea, especially from the point of view of something like robotics, where you need to have different disciplines working together. So you select the components, you design the vehicle, you put it together, you design the electronic sensors, you then program the sensors to do what you need them to do, and design the algorithms for the different carts, the different buggies to communicate. And there's a buggy in the Simon Perry building. You could have a look at it operating there. Because of our connection with the motion picture industry, we got to do some cool stuff here. In second year, in my course on computational engineering, I kind of motivate the study of differential equations by getting my friend Oliver James to talk. He is a visual effects designer in a company called Double Negative in London. They were the main visual effects house responsible for a movie called Interstellar, and they did a famous visualization of a black hole in that movie. And it turns out in second year, you know enough mathematics to figure out how to do that. So he comes and talks to students about it, and we kind of boil down the problem to a simple form, and people could actually follow how you could do something like that. So yeah, coming back to the way I think about the course program, right? We have this sort of substrate in signal processing and basic circuit design, in reconfigurable hardware, machine learning, and then we have all these applications built on that, which you get to later on in the curriculum, right? So you have audio, video engineering, motion picture engineering, I call it, robotics, cyber-physical systems, telecoms, and bioelectronics. The way we express these streams or these themes, I should say, could change from year to year, but that's sort of how we think about it now. A couple of new things have happened in the last year. Our PhD students got together and launched this IEEE student branch, which now allows 4th and 5th years to connect with the largest professional engineering network in the world. And the students kind of share experiences and also help each other about good practice in writing reports and giving talks, technical talks, and so on. And both staff and students are involved in that. So in 3rd year, like I say, you start to go into this area, electronic and computer engineering. All students start to do work in digital circuits and reconfigurable hardware design. In the Simon Perry building today, you will be able to talk to people who can tell you about these projects. And then in years 4 and 5, you start to specialize even more. We were the first university in Ireland to recognize the importance of deep learning. So we started a compulsory module in 4th year way back in 2018, which all our engineers take, and now mechanical and civil engineers are also taking it. It's so important. This area totally changed the way we think about control and about design. And if you go to that website, you could find some of the lectures online, and the early lecture is actually something that anybody could get into. So I just want to remind you about the connections we have with industry here. It's quite important, of course, for any engineering department to be connected to local industry. And like I say, right now we have more companies coming to us for graduates than we have graduates. So it's a huge growing area. Another thing that for me was very inspirational when I was in an undergraduate was getting involved with academic staff in cool research areas. Just kind of see where things go, right? So this guy here, his name is Isaiah Izojola. He is my 5th year project student. He's working for a master's, and he's working on that right now. He graduates next year. He's a big unit, right? A little bit bigger than me. He could lift 200 kilos, which is twice my weight. It's pretty impressive. And he is working on kind of re-examining what people think about deep learning and artificial intelligence. You see those skeletons? They are automatically discovered by a video processing algorithm. But you could tell the skeletons are not right, because if he was really shaking around like that skeleton, he would probably break, right? So we're trying to fix that. And the reason why we're trying to fix that is because right now in powerlifting, you need 3 judges to tell when you have achieved the right posture, and so your lift is complete, right? So by using a tool like this, maybe we could make that more accurate. And we're looking at this for other sports as well, cricket in particular. So that's a lot of fun. Another nice story is this cyber physical systems module that we launched a couple of years ago. So it brings together a lot of different disciplines. Students now work on a drone. This is a short video clip of where that project or that course started, right? So that's Stephen Roddy doing gesture control to control a drone. So we built the interface, figured out how to do gesture input, and then figured out all the control systems to get that to work. And now, in the 5th year, we have a module called Cyber Physical Systems, where you actually take a lot of different disciplines, electronic computer engineering, but mechanical control engineering as well. And students build this drone from the ground up, build control algorithms, and so take theory and put it into practice. And in our 5th year, that's quite important. So this is an example of what students could do now. All right, so that brings me to the end of what I have to say. I know I went over time, sorry about that, but have a look at this website. If you want more information, please go to the Simon Perry building. And if you forget everything of what I've said, just remember that this area is quite diverse, all right? Okay, good.